go.
We've talked about the infinite plate. And that the electric field coming off of an infinite plate with uniform charge distribution is sigma over 2 epsilon sub 0. Now the epsilon sub 0 is for free space. This assumes that there's absolutely nothing around it. I just got this infinite sheet with in a vacuum, in essence. If I take that plate and I attach it to a battery, well, no charge is going to build up on it because I've got it, it's a conductor, and I just have current just flowing right through it. I've done the battery power supply bit. Okay. So that's my positive and negative side. The electrons are going to flow out the back here, up and onto the plate, and then through the plate and on through there. So this is a rather silly design. But if I took two plates, hooked up to a battery, I'd have electrons coming on here, electrons shooting up to here, and I get an electron on this plate. And so this plate's now negatively charged, and it's going to chase an electron off the other plate, making this plate positively charged. Now that I got a lot of space on this plate, so I'm going to get another electron on here, and another electron will leave. And eventually I'll build up the electrons over here, and I will build up a lack of electrons on the other side until I have two plates that are whose charges are equal in magnitude, just opposite in sign, which I will label as Q and negative Q. So I now have the storage of charge. I have all these electrons here that need once to get over to the other side. They're being pulled towards, well, they're being repelled by the electrons on the negative side of the battery and attracted to these positive charges here. But if it's a well-designed capacitor, or even a mediocrely designed capacitor, the electrons won't go. Now, it is possible I could crank up the voltage here. At some point, they will spark across. That is the dielectric strength. I'll give you that number. And there are some interesting videos out there where people play with different things to see at what point they can burn holes through it. Now, I have all these negative charges that want to get over here. So I have this store of quick current. Now, there are a couple of uses for having the store of quick current, one of which is flash bulbs, where you want a very bright light very quickly when you're taking a picture, tasers. And I think we've talked about tasers in here. Okay, I guess it was the other group. Tasers is an example where if you touch these two leads to something that will conduct, like skin, that suddenly these charges will go zipping across into the other side. Now, if I touch it with my finger, it probably would burn across my finger there. If I touch it with two hands like this, then that potentially could kill me, as it would go across my heart. And so the heart could potentially seize depending upon the strength of my heart and the strength of the current that's flowing through it. You can take flash cameras, disposable flash cameras, and there's videos out there of people taking those flash cameras, just with minor modifications, can actually turn it into a taser. And then they try it on themselves, which is better than trying it on other people, but they try it on themselves and film it and post it on YouTube. please don't ever post yourself zapping yourself or anyone else on YouTube. But it's their thing. I guess like guy jumping in cactus. Why? I assume you've seen that video. It has, you have the look of someone of, why did you do it, or did you find it worthwhile?
I don't know. Somewhere between, bro.
I don't like laughing at other people's pain, but I laughed at his. Anyway, obviously, I digress. Now, the more voltage I put on this, the more charge I can store on this, up to a certain point, at which point the capacitor will break down. And that ratio of charge to voltage is called capacitance. Now in this particular example, I have two parallel plates, but it works for cylindrical capacitors, spherical capacitors. That ratio of charge to potential difference between the two oppositely charged plates, or spheres, or cylinders, whatever you happen to have. Let's take a look at a more specific example. Oh, let's actually talk about one of the rules. We do have a complete circuit here, because once I hook this up, I have electrons leaving here and other electrons coming in here. The electrons leaving here are not the ones that will be coming on the other side, but I do have electron flow out one side in the other. The direction of current flow was decided before they knew of electrons. It was Benjamin Franklin who pictured current as a positively charged water, some sort of fluid that flowed. And so the conventions were set up in the 1700s. And then later on, when the electrons were discovered, I think by J.J. Thomson in the 1870s, 90s, somewhere in there, it was too late to change. So I have electrons flowing this way, but the current flows the other way. The symbol for current is capital I, later on a lowercase I. And so then electrons are flowing the other direction. Some textbooks will talk about electron current. I'm not a fan of that expression, but just if you see electron current, they're just talking about the direction the electrons are flowing, which is opposite the traditional current. If I have a potential at this spot right here to be 4 volts, and the potential here to be 3 volts, if I go from 4 to 3, what's my change in potential?
1 volt. -1.
Yeah, -1 volt. If I go from 3 to 4,
1 volt.
if I go from 4 to 3 to 4,
0.
yeah. The potential between any spot and itself, potential difference between any spot and itself is 0. This is the basis of what's known as Kirchhoff's voltage rule or loop rule. And it basically says if I go on any circuit, around any complete circuit, if I start at some spot, when I get back to it, all my potential gains and losses should add up to 0. So if I have a 12-volt battery here, and I start here, and this is, you can start anywhere. I personally like to start on the negative side of a battery. That's just a Dodge-Scar thing. So if I go across, I'm going from the negative to the positive side. What is my potential difference as I go across here? Potential on the battery, which is, in this case, 12 volts. Yeah, so I gained 12 volts. If I had gone the other direction, I would have lost 12 volts. But I gained 12 volts, I go across here, I go across my capacitor, and I end up back where I started. So I should be at 0 here. So if I had positive 12 volts going this way, what do I have going this way?
-12.
Yeah. I gain 12 here, I lose 12 going here, and end up back at 0. This idea of the voltage and loop rule we will exploit for many chapters. Also notice I'm going from the positive to the negative side of the capacitor, I lose potential. Also, I know that my electric field goes from plus to minus, so my electric field is moving to the right here, and electric field moves opposite the direction of the change in potential. So if the electric field moves to the right, my potential moves in that direction. And perhaps we haven't gotten to that part yet. Did we? All right, so I have this capacitor here. I have this potential. Well, let's take a look at the electric field. Got my positive Q here, I have my negative Q there. Now my electric field is going across like this. The magnitude of my electric field between them is going to be the surface charge density over epsilon. So not for now. And that is just the charge divided by the area. I know that my change in potential is equal to the negative integral of E dot d Rx, whatever you happen to be dealing with. And in this region here, when I'm going from the left side to the right side, that's my electric field. Actually, it's electric field strength. As I'm moving from the positive to the negative, my electric field is in the direction of my differential here, dr. And my electric field is constant between these two infinitely large plates. And so since E is constant and in the same direction as dr, this becomes negative E integral dr, which would just be the distance between the plates. We'll sometimes refer to this as the ED equation. Now, between the calculus and the simplified version of it, if the electric field is constant, I could write my change in potential is the negative of the dot product between electric field and my displacement, XR, whatever you're using. But again, these assume the electric field is constant with respect to space. So dE dx is equal to 0. Not commenting on whether the electric field is constant with respect to time. All right. So my potential here is equal to the negative ED. Well, here's my electric field strength right there. So negative, well, I'm going to drop the plus and minus for right now. So that's just Q D over A epsilon sum naught. So if I have these parallel plates in acting as a capacitor, in other words, a parallel plate capacitor, then my capacitance is equal to Q divided by my difference in potential, which is Q D over epsilon naught A. Q's cancel out, and what I'm left with is epsilon naught A over D. We need to extend this one step further by not pretending that it's a vacuum in between. If the space in between here is not a vacuum and air is close enough to a vacuum, then In other words, I put some insulator in here. That insulator is known as a dielectric. So I put a dielectric in here. Dielectric is an insulator. And my formula changes to epsilon A over D. We drop the subscript. Now, epsilon sub naught, as you know, 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So we're dealing with really small numbers there, and what the powers that be decided is, I don't want to have to remember all that stuff. Let me see can you give me a smaller number to work with? And yes, you can. They define the dielectric constant a kappa, not a K, it's a kappa. And that is the permittivity of whatever the material is divided by the permittivity of free space, the smallest value epsilon can be. Therefore, epsilon, the permittivity, is equal to kappa times the permittivity of free space. And so my equation here now becomes C equals kappa epsilon sub naught A over D. So we have two formulas here. So for all capacitors, we have capacitance is equal to Q over delta V, where Q is the charge on the positive plate and delta V is the potential difference between the plates. For a parallel plate capacitor, C is also equal to kappa epsilon naught A over D. So let's just do a quick and dirty plug and chug. I have a parallel plate capacitor. We'll just take this one right here. I have a parallel plate capacitor with, I don't care about that. Let's make this 10 meter by 10 meter. Each plate is 10 meters by 10 meters. And the distance between them is 0.1 meters. And we've got A, D, and so okay, we're good to go. What's the capacitance? Well, I got nothing in between them. Parallel plate capacitor, so I can do this. I got nothing in between them, so kappa is equal to 1. No units, just 1. Epsilon sub naught, 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared, times my area, 100 meters squared, divided by the distance between them, 0.1 meters. And you end up with 8.85 times 10 to the negative 9th. What?
Farad, wouldn't it?
Be what?
Would be farad, wouldn't it?
It would be. They could also be, if you looked at just what we have here, that would be coulomb squared per Newton meter, or coulomb squared per joule. A joule per coulomb is a volt, so that's a coulomb per volt. Or farad.
Why is the dielectric constant 1 again in this problem?
Because I've got nothing in between the plates.
Would that be kind of a given thing in a problem, or would
Yeah.
would ways to find the dielectric constant as well.
I'll give you one or the other. In the lab that you'll do on Monday, you will find kappa for various types of materials. Farad, named after. Okay. No one wants to guess Mr. Farad? It's not. It's named after Faraday. Faraday was too big. They had to chop something off. Okay. If I stuck a dielectric in between there with, let's just say kappa is equal to 2. So a dielectric constant of 2, what would be the capacitance now? Yep. Now, what the dielectric does, it's an insulator, so we don't have charges flowing through it, but we do have polarization going on. So normally in a dielectric, there's random plus and minus charges. So plus, minus, minus, plus, plus, minus, plus, minus, plus, minus, and so forth. When you introduce the electric field to it, the protons want to move away, but they don't really move much. The electrons are attracted in the opposite direction of the electric field, so the electrons all move. So if my electric field's moving this way, my electrons move over there, so I get negative plus, negative plus, negative plus, negative plus, negative plus, negative plus. And each one of these has its own electric field because it's polarized. We have an electric field that is now going in this direction.